This lecture is on overview of experimental stress analysis, and this slide shows in nutshell what experimental stress analysis is all about. And what we see here is stress patterns observed in a 2D model of a human femur. So, you get stress information in stress analysis, and you also get displacement information in stress analysis. And what you find here is, for a circular plate clamped at the boundary with a central load, you get the displacements, and you can also have the slope, you can also get curvature. But what you will have to appreciate here is, for each of these information you need to use a specific optical arrangement. You do not get them in one shot, but you have to have effort to do that. And what you see on these two corners show that you need to use physics in applying experimental techniques. So, what is done is, any physical information which could be exploited for measurement is identified, and that is translated into an experimental technique. And what you see here is a cusp in a teacup, and this you see as a silver line. What happens is, when light gets reflected on the curved surface, it gets reinforced and you have a cusp, and this can be seen on any shallow filled containers with appropriate lighting, and this phenomenon is called caustics. And this physical information is exploited in a technique called method of caustics, which is used for measurement of high stress concentration. How it is done, we will see as part of the course. And what you see here is another down to earth example, where you see in the case of a fan, when you have two grids superimposed, you see a nice moving patterns, and this is called moire, and this is used for measurement of in plane displacements, out of plane displacement, and so on. So, what is emphasized here is, when you have experimental stress analysis, I can measure stress information, I can measure displacement information, I can also measure strain information, though it is not shown here. And what is emphasized here is, for each of the experimental technique there is a physics behind it. So, you need to appreciate the physics, understand how this physical information is exploited, and that is what we are going to see in the lectures to follow. But before we proceed further, we need to know what is stress analysis all about. So, the term stress analysis in the complete sense encompasses the determination of 6 stress components. Why they are 6? Why do I say that you have 6 stress components? Suppose I take a member like this and then apply a tension, you all know the stresses are developed, and what is the value of stress? Someone can answer. Suppose I apply the load as P and area of cross section is A, what is the value of stress? Where are 6 components? You are only saying only 1, and what you have in this simple example problem is, stress is a tensor of rank 2. So, you have 9 components. Of the 9 components, because of symmetry, you have only 6 independent components. So, in a simple tension test like what you do on a slender member, you evaluate stress and it appears to be a scalar, P by A appears to be a scalar, and that is what you have learned in a simple course in strength of materials. But what you should change your thinking is, go back and fill in the components in the stress tensor. So, what you find is, I find one stress component, all other stress components are 0. So, that is why you have, because stress is a tensor of rank 2, you have 6 independent components. So, when I say stress analysis, I should know stress components. Then I also need to know strain components, and strain components are again 6, because strain is also a tensor of rank 2. So, I need to get stress components, I need to get 6 strain components, and it is also desirable that I get displacement components, and displacement components are 3. And what way I want this information? Suppose I take this rod and I pull it, I want this information at every point in the model. So, what I want to do is, for every point in the model or component, I want all of this information, and in this simple case the stress component is only one. If I keep it, it's sigma y. If I keep it horizontal, you label it as sigma x. If you have x and y as horizontal and vertical, you will have this as sigma x stress component, or you will put it as sigma y stress component. So, what you need to understand is, stress is a tensor of rank 2. So, whatever the kind of loads that you apply, you should be able to identify the components, and what I want is, I want this information for every point in the body. Right now, let us not worry about the values of these near the place where I hold them, where I grip them and do it. Away from the point of loading, we will worry about it. And when you say this P by A, I know it at everywhere and it is constant, and such a solution, if I give the xy location and I am able to find out the values of stress, I call that as closed form solution, because at every point which I want to find out, I have the answer. Can you get closed form solution for all problems? It is not so. It is only a luxury. For certain problems, you are able to get all the 6 stress components, 6 strain components and displacements, and in certain class of problems you are satisfied with near field solution, particularly in the case of problems with crack, where fracture mechanics is focusing this, you get analytically solution close to the vicinity of the crack tip. And from a design point of view, you are happy with even point solutions. You would like to know where is the maximum stress when you want to find out stress concentration, when you want to go for optimization. You also want to know where is the minimum stress, because from there I can scoop out the material. So, what you have to understand is, the term stress analysis in its complete sense encompasses determination of 6 stress components, 6 strain components and 3 displacement components, and it is a luxury. So, we have to go for that kind of solution which you require for a problem on hand. Always you do not require all these 15 components. And how this stress analysis can be carried out? You could do this by analytical methods, you could do by numerical methods, or you can also do by experimental methods. Can you take a view that I will always use analytical method, or I will always go to numerical method, or being an experimentalist I will use only experimental methods? We cannot take that kind of a prejudiced view. Each approach has certain characteristics that could be effectively exploited. Few of this we will see as we go by. In a very complex problem situation, one technique may not be sufficient. You may have to use a combination of analytical, numerical, or numerical and experimental, and that analysis is known as hybrid analysis. And what we are going to do now is, we will see one by one what analytical methods, for which class of problems, why do you do analytical methods, and what is the advantage of a numerical technique, and when you go to experiment, in which class of problems experimental methods are ideally suitable. That is what we will see now. And once you come to analytical methods, what is the advantage here? These are useful to get a conceptual appreciation of the nature of stress fields. If I want to know, I take a member and I pull it, I know that it is subjected to tension, and I do the bending, and I want to know how the stresses are developed in bending. But when you look at whether it is strength of materials or theory of elasticity, the range of problems that could be solved is limited. And the broad classification of the analytical methods, we call them as strength of materials and mechanics of solids. and in mechanics of solidity you could classify that as theory of elasticity and theory of plasticity. And what we see here, they are very useful in getting a conceptual appreciation of the nature of stress fields, but the range of problems that could be solved is limited. And you have all done a preliminary course in strength of materials, and do you know in strength of materials what is the basic assumption that has been used in solving the problem on hand? Can any one of you answer?
Plane sections remain plane before and after loading.
You remember that that has been taught in your earlier course? Okay. No, the basic what you want to know is the basic information that you use for attacking the problems. And what you find here is, so one of the basic assumption is plane sections remain plane before and after loading, and with this what we have solved? We have solved a large number of problems which are slender in nature. It is very important. Suppose I take a plate and then stretch it like this, I have no problem. Suppose I put a hole there, I cannot do it with strength of materials. The moment I put a hole, the assumption plane sections remain plane before and after loading no longer exists. So I have to be careful. So that is why you always solve problems that are solvable. So in a strength of materials course, what you get is, you understand how an axial member, a bending member or a circular shaft subjected to torsion supports the load. In the case of axial member, what do you understand? Suppose I take the cross section A and suppose I apply the load P, how the force is distributed? It is uniform, the entire cross section participates in the load sharing. On the other hand, if you go to beam under bending, what happens? What is the difference between an axial member and a member that bends? So this is where you have the answer. So what you have here is, I have the member which bends and I find that stresses are varying linearly over the depth. And what you find, this is a very famous Flexure formula, and what way you did it? You never went and solved differential equations. You cleverly avoided solving differential equations and you hide behind the assumption plane sections remain plane before and after loading. And if you watch this problem, this is also very clearly shown that you have the end loads here, but you are only looking at a region which is interior to that, where you have only pure bending is applied, and the discussion is confined to pure bending. If I go to cantilever, I have a shear and plane sections do not remain plane before and after loading. They are not coupled, so you are able to still live with Flexure formula. And if you go for deep beams, you have to bring in shear effects. So in a first level course, you will learn how an axial member supports load. That is why you have lot of trusses that is being used for in stadiums and very large halls. So you effectively utilize role of material completely, because all the material contributes to load sharing. The moment you come to bending, you understand that stress is varying linearly, so the inner core is not contributing to load sharing. And what is seen when you go to how this is used in design? So if you go and see a rail cross section, you do not have a square block, because you know that this is subjected to load on the top face, and you know it is essentially transmitting a bending load. Since the inner core is not participating, you have removed the material. So what you have done is your analytical approach to problem, you have not solved the problem of rail to start with, but your bending understanding that what you have, the stresses vary linearly and inner core is not contributing, is effectively utilized in arriving at a shape of the rails. Okay. And now what we will see is at an introductory level the approach is attractive, as one could understand how an axial member, bending member or a circular shaft subject to torsion supports the load. And once you come to circular shaft, you all know people use hollow shafts, very similar to bending, there the shear varies linearly. So, in pure torsion you only talk of a circular shaft subjected to torsion. Suppose you have a rectangular shaft subject to torsion, that is shifted to the next course, it is not taught in the first level course, because we always want to have a very simplified approach to problem solving, and we have cleverly avoided solving differential equations. But nevertheless we have understood how an axial member supports load, what happens in the case of a bending, what happens in the case of a torsion. So, analytical methods are very crucial in giving a conceptual appreciation on very simple problems, but you will restrict to class of slender members, you will not go to any other class of problems, and this is very effectively used in design. If you go to the second level course, you always use the design based on very simple idealization based on strength of materials. So, what you find here is the knowledge of strength of materials opens up the learner on the role of stresses in designing members, like I have shown you that you have the rail where you have removed the material from the central portion because it takes the load only on the top and bottom fiber maximum. Whether you have understood or nature also has understood solid mechanics, and if you go and see, you have bones, bones are hollow, the inner core is where you have bone marrow, where you have hemoglobin is developed, and that has to be protected. So, you have a hard shell, and your bones, if you take a thigh bone, it is subjected to bending, and in appropriate loading it will also have some level of torsion. So, nature has already understood that when it has to resist bending or torsional loads, it can optimize its structures beautifully, because bone marrow is a very soft material, and if you really go and look at bone, people now say that it is a functionally graded material, it is not even just hard and soft, it is a functionally graded, and they say tooth is also functionally graded. So, nature has understood all this mechanics, solid mechanics, and utilized it in many of its structures, and as humans we go try to unravel it and embed it in the form of mathematics and develop as engineering tools. Okay. Now, what happens, suppose I the basic restriction is I assume displacements in the case of strength of materials, and you can't live with that. If you go to a fluid mechanics course, they start with differential equations, they do not have any problem where they avoid differential equations. Only in solid mechanics what we find is you can have one full course without touching differential equations, and only in the second level course you relax this, you do not make assumption on the displacement, but you evaluate displacement as part of the solution, and this is what you have it in mechanics of solids. By relaxing this, if you find whether you have been able to solve all problems on hand, which is not so, the solvable geometry include those for which boundaries could be easily identified by a coordinate system, so that the boundary condition could be easily specified. Now, I have shown that you have a plate with a hole, I cannot solve plate with a hole by theory of elasticity unless the hole is sufficiently small, and what you have here is a photoelastic model, and here you have a plate with a hole and plate with a very small hole. From a mathematical point of view, it is possible to assume or idealize that this is a small hole in an infinite plate. Physically it is finite, but mathematically it could be modeled as infinite, and you would be able to find out analytical solution for this using theory of elasticity. On the other hand, if I take a model with a slightly larger hole, then this solution is no longer valid. I have the same width, the width is same, in one case it is very small hole, in another case the hole is about 10 to 12 millimeters, and this is comparable to the width. So, this becomes a finite body problem. So, when I go to theory of elasticity, where I am able to idealize, I look at a situation where I remove the restriction on displacements and I evaluate displacement as part of the solution. Even there I need to have infinite boundaries for a problem like this, only then I will be able to solve. Mathematically the distances are far away, but physically it could be a very small hole. This closely resembles, and this solution is possible. And plate with a hole is a very important problem. You all learned, see in one of your design courses, when I have riveted joints, I have a series of holes. So, the idea here is, as an analytical method, you have been able to find out the presence of a hole, how does it influences the stress field near the hole. You are able to get an analytical expression, and this will be a function of x and y. So, if you plug in x and y, you will be able to find out the solution, you will be able to find the solution at every point in the domain, okay, which is not the case when I take a finite geometry. This finite geometry, it is not possible to solve by theory of elasticity. On the other hand, other geometries, like suppose I have a circular disc and a diametral compression, this you get closed form solution from theory of elasticity. And compare, I have a axial member, I pull it, I can do it by strength of materials, but the same axial member, suppose I have a hole, I cannot solve it by strength of materials, I have to depend on theory of elasticity. Even in theory of elasticity, the hole should be as small as possible, okay. And on the other hand, even if you change the geometry, you can't do it by, I do not have a hole here, but the geometry is changed, because the way I apply the load, plane sections do not remain plane before and after loading. So, if you look at, when I move from strength of materials to theory of elasticity, I have enlarged my domain of solving problems. Strength of materials has given me a very good approach, wherein without solving differential equations I could understand axial member, bending and torsion. When I go to theory of elasticity, I could find out what is the meaning of stress concentration, and I can also solve a class of small problems where I am able to find out the boundary conditions and then apply it carefully. So, you have a large class of 2-dimensional problems have been solved. I have a disk, you have a solution, but if you look at a 3-dimensional problem, and if you want to approach and find out whether you have analytical solution, those problems you can count them in fingers, they are very few. So, the problem is very complex, and I want to find out, I want to take a spanner and I want to tighten a nut, because this has arbitrary geometry, I cannot approach it from theory of elasticity and get the solution, and this is what we do day in and day out. So, what you find here is, even though you have methods which provide you conceptual understanding, if I go for arbitrary shape, numerical methods come very handy, and you are able to get the solution at least approximately for arbitrary geometry. So, that is where you find the numerical methods are very attractive, and you have many numerical methods. Many of you might have done finite difference, then you have most versatile finite elements, you have very many packages available for you to attack a problems, and you also have boundary elements, and very recently you have mesh free methods that have come. And what you find is, when I am having a numerical approach to problem, the numerical model has to be validated. Once, unless numerical model is validated, if the boundary conditions are not verified, you are solving a different problem. So, for any numerical approach, you will have to validate whether the procedure is all right, but the greatest advantage of numerical method is, once the procedure is validated, it is an ideal way to do a parametric analysis. In a design, if you have several geometry factors, you would like to vary them, or you like to change the load case and find out how the system is going to behave. Conducting experiments for each one of the configuration would be difficult. So, you do an experiment, verify the discretization, verify the boundary condition, then do a parametric analysis by a numerical approach. And once you come to experiments, what do you see? Very similar to numerical methods, experimental method is applicable for complex geometry, absolutely no problem. And once you come to experiment, you will also have to look at two different things. Am I working on a model or am I working on a prototype? So, you can do the experimental approach on prototypes or on models. And another area where experimental methods are the ideal choice is in the area where you have assembly stresses or residual stresses. Now, I take a very simple example of a chain, and this you have it in your bicycle. It is also used in power transmission, and in practice what you have two sprockets on either side, and this is subjected to essentially tension in actual service. Okay. And now what I have here is I have an element taken out of this chain. I am just holding it. Are there any stresses in this chain? How many of you say no? How many of you say yes? There is one person who says he is stressed, the rest of the class say it has no stresses. See, you have to know how this component is fabricated. Suppose I take a block of material and then I go to CNC machining and then machine out this, that is one thing. And how it is done is you have essentially plates, and these plates are brought together by putting the appropriate bush, and the bush has to stay in place. So, you have a oversized bush and this has to be inserted. So, this is done with an interference fit. So, apparently I do not have any external load on this chain link, but because of the way it is manufactured, you have stresses developed, you have a bush here, you have stresses developed very prominently here, and it is comparable to the service loads. The stresses developed are not small in value, they are comparable to the service load. So, what you need to understand here is it is a very complex problem, and this is where many service failures are reported. Service failures in the field are reported because of residual stresses and also assembly stresses, and experimental methods come in very handy for solving problems of this complex nature, because there are many issues that go into this. You have the bush, and bush may not be perfectly cylindrical, and another one is this is a body which has finite geometry. You have a finite geometry and this is an arbitrary shape. Finite geometry I cannot go and approach by finite element by theory of elasticity. Definitely I can approach it by finite elements, absolutely no problem, but there I have to apply the boundary conditions. What the information I may not know from a production shop is this may not be perfectly cylindrical, this will have a variation. So, suppose I put it and then do an experimental analysis on this component directly, which acts like a prototype, then I capture all the manufacturing variations that has gone into the fabrication of this. Whereas if I do a numerical analysis, I would take this as a perfect cylinder, I would not have model if there are any fine undulations on the surface of it, and such variations do exist in actual practice. So, what you find here is for conceptual understanding numerical analytical methods are needed. For complex geometry you have to go in for numerical methods, but to know the truth you will always have to depend on experimental methods. Okay. So, experimental methods are the best choice to solve such problems, and the study is done on the prototype. And in model studies you have a difficulty, because in model studies the challenge lies in designing appropriate loading jigs. So, if I do not design the loading jig appropriately, then I am not solving the problem that I have to solve even by experiments. I said in numerical techniques, if you do not specify the boundary conditions, you are not solving the problem that you have to solve. The same defect exists even in the case of experimental methods when you have to work on models. When you have to work on prototypes, the approximation is as close as possible to reality, but when you have to work on models, you have to load the model. Now, let us see one simple example. I have this rod and I want to pull this. I can pull it by grips. I can have solid grips and then pull the rod, and I can also pull the rod by another method, which is what usually do. What you do is you have a sling, you have a pin, so you pull it with the pin. It also has a certain level of self alignment, and if you really look at what is the stress distribution near the close vicinity of the hole and the way I grip it, these two are different, but our interest is I want to have axial force in this member, which could be done by numerous ways, and one way of doing it is putting a pin and sling and then pull it, another is put a grip and do it. So, I am not really solving a problem that I have to do what I have in actual practice, and this is where you have this famous Saint-Venant principle that is required. So, you in many instances in designing loading jigs, you use Saint-Venant principle. What it says is, at distances away from the point of loading, the distribution is similar to what we finally want. So, you will have to use Saint-Venant principle and design your loading jig appropriately, so that it simulates service load condition as closely as possible. Then what you have? There is also another difference. See, in the first I showed axial member pull, you have P by A, you have the stress component, rest of the stress components are 0. If you want to find out strain, you can easily find out, because you have this you have readily available mechanics of solids equations, you have stress strain relations, strain displacement relation. So, once I find out stress components, I can find out the strain, I can find out the displacements both in analytical and numerical methods. This is primarily because I know all the stress components by an analytical method, then I proceed. In a numerical method also, when I solve, I get all the stress components evaluated, then I go for strain and displacement, which is not the case in the case of experimental technique, because experimental technique exploits a physical principle for measurement. So, that physical principle imposes certain restriction what you can measure in an experimental technique. Suppose I measure stress, I cannot measure all 6 stress components. I can measure only a particular stress component or a combination of them, which is dictated by the physical principle employed in the technique. On the other hand, you have an advantage, it can work on prototype, it can work on arbitrary geometry, it can find out residual stresses, it can find out assembly stresses, but the restriction is I do not get all information in one go. So, this is one restriction that you have to live with, and once you come to experimental methods, there are many experimental methods available. They are broadly classified as whole field techniques and point by point methods, and if you look at whole field techniques, they are essentially optical techniques, and you have a great many of them, and newer techniques are also being developed day after day. And when you look at whole field techniques, one of the very popular and widely used experimental method is technique of photoelasticity, and we would see later what these experimental techniques give directly the information, what information it can give directly, and essentially photoelasticity gives sigma 1 minus sigma 2 contours. and you have moire that essentially gives displacements, and you have brittle coatings that gives you direction of principal stress. So, for each one of the experimental technique you get a particular kind of information, and even if you use that the particular experimental technique, if it gives more than one information, you should use different optical arrangements to get it. So, you do not get anything free, you have some advantage, some disadvantage that they go together. So, it is a user who has to decide what aspect he will exploit and then find out which combination you will try to use for solving a problem on hand. And you have holography. Many of you must have seen holography as a sticker on many of the products. It is used for mostly as a security device, but it is also a very good experimental technique, and you would essentially get the displacement vector. And you have speckle methods, which is a variation of holography, and one of the very recent experimental technique is digital image correlation. This has an advantage of working at multi-scale. Specimen preparation is very simple, surface preparation is very simple, and it exploits the computers to the fullest extent for measurement of displacement. Then you also have a technique called thermoelastic stress analysis, and what you have is, when you have a model and then put a load, when I put a cyclical load, the temperature changes. The temperature change is very, very small, and those are measured by a non-contact approach, and you have a thermoelastic stress analysis. And you have a point by point technique, and what you have here is the widely used strain gauges. I say it is widely used, I also caution it is a widely abused technique, because people in a strain gauge, people have to paste a strain gauge, and pasting a strain gauge is such a boring exercise, and you have to be trained in pasting strain gauges. If you do not paste the strain gauges properly, you measure anything under the sun. So, you do not really measure what the system shows, you have error sources. So, unless you handle the technology behind strain gauge instrumentation right from pasting onwards, you would not measure the quantity that has to be measured correctly. And you also have special techniques. As I mentioned in the beginning of the class, we saw there is a optical phenomena where light gets reinforced and you get a silver line. You have this as phenomenon of caustics, which is used in high stress gradient problems, like when I want to find out what is the stresses developed in the vicinity of a crack. This is a very useful technique, and because of Poisson effects, the specimen behaves like a divergent lens. And caustics is can be classified as a point by point technique because it gives only one information, and you have a field information in a coherent gradient sensor, which is a variation of caustics. And you should also appreciate that newer techniques are constantly added, and as I said earlier, a single experimental method or arrangement rarely provides complete information of stress, strain or displacement fields. It may give a particular kind of information. If you are satisfied that that information is good enough, then one experiment is sufficient for you to get the answer you wanted. If not, you may have to use a combination of different experimental techniques and go and evaluate the parameters that you want to do it for your analysis. And as I have mentioned earlier also, what is the physical principle behind a technique and what aspect of its feature is exploited decides the what an experimental can give. So, I need to know the physics behind it. Another aspect is what is the physical principle used and the technology used to translate the principle of measurements decides the accuracy of the experimental technique. Because if you go to photoelasticity, earlier we were making measurements manually, now you have image processing techniques available. So, with the technology I can refine the measurements further. So, you need to know what is the physics behind it. Suppose I go to the image correlation, the size of the speckles matters, and there is an inherent difficulty when you want to go for very low value of strain measurement. So, you have the physics, what is the physics that you use and what is the technology that is used to exploit this, both have to be in synchronization for you to arrive at a accuracy of particular kind. I can make measurements using, suppose I want to measure the length of this room, I can go and take a tape and measure it. When I take a tape and measure it, I am going to say so many centimeters. On the other hand, if I want to have very fine measurement, then I can go for laser based measurement technique, where I will say in terms of nanometers the accuracy of the length, same length measurement, by depending on whether you use a scale, whether you use a tape, or whether you use a vernier, or whether you use a screw gauge, or whether you go to optical method, the level of accuracy is inherent in the measurement approach and also the tool that you use for it. So, as a stress analyst, you have to decide whether you want all the 6 stress components, all the 6 strain components, all the 3 displacement components at every point in the model, or only a particular kind of information at a few locations. So, this decides the selection of an experimental technique. And for this course, I would essentially use my book on experimental stress analysis, e-book on experimental stress analysis. This has been developed at IIT Madras and published by IIT Madras, and this contains more than 100 hours of teaching and learning material, and this book is dedicated to my lineage of teachers and pioneers in experimental mechanics across the world, and this will be the core book that I will be following it, and other books that you require for self reading and reference I would give you as we go by in the course. Are you clear that what is the fundamental difference between an analytical approach, numerical approach and experimental approach? Analytical approach provides you conceptual appreciation of what is axial load supporting members, how do they behave, in bending how the stresses vary over the depth, in shear how the stresses vary. That understanding is very crucial in translating many of the design what you see across. They could be simplified to any one of the slender members as a first approximation, and you can get some insight what is happening. But if you want to get a detailed solution, you have to go to theory of elasticity, where you do not have the restriction on the displacements. In you have a simply connected and multiply connected problems. In multiply connected problems, you have to bring in uniqueness of displacement as a input, otherwise you cannot solve the problem. But leaving that apart, you do not put any restriction on displacement. You evaluate by solving differential equations, and when I have a complex geometry, I can always go and attack the problem from numerical approach, but numerical approach has to be handled very carefully, because you may go wrong in understanding and implementing the boundary conditions. So, any numerical approach has to be validated by experimental inputs. Once you validate the numerical approach, they are the ideal choice for a parametric analysis. On the other hand, when you come to experiment, if you use the technique very carefully, you really get the truth, and you can work on prototypes, you can work on models, and when you work on prototypes, you are very closer to reality. In model studies, you have to be very careful in designing the loading jigs, and if they are not designed properly, you may not really simulate the actual service loads. So, that will also be erroneous, but you need both. You need to have prototype studies, you also need to have model studies, and you will also have to look at whether a particular experimental technique can be applied for both prototype and model studies. Because if you look at photoelasticity, one version of it can be applied on models, a variation of that can be applied on prototypes. So, the technique can be applied both on models as well as prototypes. So, you have to choose depending on the problem on hand what is the way that you would go and select this experimental technique, and an experimental technique by itself will not give all the information of what the basic stress analysis is all about. It will not give all the 15 components. What component I get is dictated by the physics behind the experimental technique. So, in this course we would pay attention on what is the physics behind each of these experimental technique, how these have been exploited, what is the technology used, and what is the do's and don'ts in employing an experimental technique. That is what we are going to see in the classes to come.